Hello, my name is Igor and you are watching my Tech Fun. I have two very interesting filaments for this video and they are sent to me by the Filaticum. A few weeks ago I did a review of their model and foam filaments, which are mostly designed for aesthetic printing, and these are PLA Advanced and Engineering. Now let's talk about PLA Advanced. First, a question: do you know why would you like to print PETG instead of the PLA? Well, there are two main reasons, and one, that the heat deflection temperature of the PLA is a little bit above 50 degrees Celsius. This means if you forget your PLA part in a car on hot summer day, probably it will deform. The second is less familiar, is the creeping. Now, PLA is actually a very strong material, in most cases stronger than PETG and ABS. And on 20 degrees Celsius, or room temperature, it doesn't creep. But on 30, 35, it will creep, this means deform under the constant load. Now the PLA Advanced resists to temperatures up to 85 degrees Celsius according to the website, so this is between PETG and ABS. Also they claim that it is stronger and more durable and less brittle material, and it has excellent layer adhesion. So if these claims are correct, basically this is much better solution than PETG, and the printability is actually like PLA. Now let's talk about engineering material. This is PLA-based filament for industrial applications, so completely new category. And on Hung Expo, I got approximately 10-meter sample filaments from them, and I did that temperature test, and this sample started with deformation above 150 degrees Celsius. And then I wrote them back that I'm ready to do a deeper research of these materials. And then I got those filaments for testing. And I will do that regular mechanical testing with these filaments, so the results will be comparable not only between these two materials, but also they are comparable with those which I did in earlier videos. They also claim that it has excellent impact resistance. It doesn't warp, which is again big advantage compared to the ABS. It has matte finish, and they also claim that it can replace metal, but I'm not sure about this. About the engineering PLA printability, theoretically it should be printable like any other regular PLA, except that it requires bed temperature up to 100 degrees Celsius. And I had some problems when I was printing that specimen for temperature test, because PLA usually use a maximum part cooling fan, and it cooled down the bed temperature. It couldn't hold 100 degrees Celsius, and I got the bad thermal runaway protection error. And my solution was to reduce the part cooling fan to, let's say, 50% or 40%. But other solution would be maybe to reduce the bed temperature to, let's say, 90 or 85. But in that case, probably I have to use some glue stick for better adhesion. But we will see. Let's start first with the PLA Advanced. It has a protection in this foil, but it is not vacuum packaging, and I cannot see any silica gel inside. Well, there are several holes for locking end of the filament, and I'm using some kind of scale to see how many filaments we have on the spool. This is the gypsum filament. I really like this one for the modeling. I'm starting with temperature tower from 220 degrees Celsius down to 190 degrees Celsius, and the bed temperature will be 70 degrees Celsius. Well, the first layer will go down very correctly, so I hope I will not have a problem with the adhesion. It started with the second element at 210 degrees Celsius, and so far this looks great, so absolutely no stringing, the bridge came out perfectly, and also the overhang on higher temperatures, so probably there will be no problems with the lower temperatures. Except I worry a little bit on printing on 190 degrees Celsius. I don't really like to print on so low temperatures, not even the PLA. This is the last element on 190 degrees Celsius. The printing looks okay. Only once so far I heard a click from the extruder, probably more resistance in the nozzle. Maybe you can hear now the clicking of the extruder. So definitely this is too low temperature, but I will let it finish now. Okay, the printing is finished, and I can see the last element was not printed correctly, but I will show you that in a few seconds. First I want to check the bed adhesion. Okay, which is great, like a regular PLA. And this is the temperature tower. So on every element, the overhang and the bridging came out perfectly. Only problem I can see on 190 degrees, so you can see this wall was not finished, and I can see some under extrusion here on this candle. So definitely 190 in my case is too low for this filament. Anyway, I don't recommend to print on 190 because you will get better adhesion if you print at higher temperatures. All test objects are printed once on 215 degrees Celsius on the nozzle, 70 degrees Celsius on the bed, and this will be approximately 3.5 hours printing. 2 more hours of printing, but looks everything is okay so far, so it looks like it is really printable like any other regular PLA. And 2 last objects are these printed in vertical position for the layer adhesion test. And now Engineering PLA. Let's open the box. And it is packed in this foil, but it's not vacuum packaging. It's a nice blue color. And I will print the temperature tower from 230 to 200 degrees Celsius. And this is not really the direct comparison of 2 filaments, so I decided to print this one on ND3 S1. And as I mentioned on Plus, I had a problem because the bed was heated to 100 degrees Celsius, and with PLA maximum cooling cooled down, and I got the thermal runaway protection on the bed. Here probably I will have a similar problem, so I reduced the bed temperature to 90 degrees Celsius and the maximal cooling to 60%. The first layer goes down very nice. The first element on 230 degrees Celsius is printed, and this printing is perfect like any other regular PLA would be. This is the bridging moment. This is the third element on 210 degrees Celsius. Interesting, I can see a little bit more string in 220 degrees Celsius, but on first tower that stringing was not there. But I will analyze this temperature tower later. And one interesting information, that I was in a conversation with the Filaticum, and they mentioned that I could get a better printing if I would print inside the enclosure, but this is PLA, so basically most of the users probably would like to print this on open printer, so that's what I will do. And maybe just the layer adhesion test I will repeat with the objects printed inside the enclosure. Printing is finished, let's remove the object. And actually this printing looks great, perfect overhang, and the bridging, only I can see a little bit more stringing than I usually see on the PLA. But if this will be the biggest problem, I don't mind, because this material has great specifications according to the website. So I think I will print all test specimens on open printer, and as I mentioned earlier, only the layer adhesion test will be reprinted inside the enclosure too. And since printing of the temperature tower went so smooth, I decided to print all test objects at once, and this will be approximately 5 hours of printing. And I'm printing these test objects on 225 degrees Celsius, and the bed temperature is 90 degrees Celsius, and the cooling is reduced to 60% max. And the first layer laid down perfectly, so I hope I don't have to supervise it all the time, because I have to leave for the 2 hours now. After 2 hours, printing is approximately at 50%, and it looks okay so far. And last 2 elements printed vertically for the layer adhesion test. And I need one more important printing from the Engineering PLA in black color. This is the sample filament I got from them on the Hung Expo, and this material will be perfect for this. It's a flange rod for Plus MRCS, and this is the only 3D printed part which is not from PETG but from ASA, because it is too close to the hot end. And I noticed in my case, inside the enclosure it deformed a little bit, so this Engineering PLA should be perfect for this object. Support has to be removed and it's ready. And it's time for mechanical testing. I am starting with tensile strength test. This test object is printed in horizontal position, and the smallest cross-section area is 4 by 4 mm, and I'm starting with PLA Advanced. And now Engineering PLA. Almost all test subjects broke on smallest cross-section area, except this one here with the Engineering PLA. I hope everything is okay with the layer adhesion, but we will find out in the next experiment. Now the layer adhesion test, this test subject is printed in vertical position, and again the smallest cross-section area is 4 by 4 mm, and I'm starting with PLA Advanced. And now Engineering PLA. Well, they all broke properly on the smallest cross-section area. Even for the feeling, the PLA Advanced was stronger, but maybe I could raise the temperature with Engineering PLA, or maybe it is really better to print inside the enclosure. I'm not sure at this moment. Now, that layer adhesion test I want to repeat with test object printed inside the enclosure using the same parameters. It's a little bit hard to see, but after approximately 20 minutes the temperature inside the enclosure is 44 degrees Celsius. The printing is finished and the temperature went up to 47.7 degrees Celsius. And repeated layer adhesion test with objects printed inside the enclosure. Well, at this moment I don't know the numbers, but even for the feeling this was much stronger, but one test subject didn't even broke on that smaller cross-section area. And now the shear stress, the diameter of this test subject is 5 mm, and as you can see it will be sheared from two sides. And again all test subjects were sheared properly on those two cross-section areas, this means in 3 pieces. 3-point bending test, distance between supports is 50 mm, and I want to record the load at 2 mm deformation and the maximal load. Well, for the feeling, the PLA Advanced was very brittle and broke very suddenly, until the Engineering PLA, well, partly it broke, but here it just deformed on one layer. I'm very curious how will they perform on the impact test. And now torque or twist test. Usually I get very similar results like with the bending test. I have these test objects 6 mm in diameter. This side goes into the vise and this side goes into the digital torque meter. And I want to record the load at 90-degree angle and the maximal load. 1.7. 1.8, what is the peak? 1.5. 1.5 was the peak. And this is how they broke. Much nicer break was with the PLA Advanced, and this is typical sign of the weaker layer adhesion. And now let's see how brittle or tough are these materials. This is my equipment for IZOD impact test with a half kilogram hammer, and I'm starting with the PLA Advanced. PLA Advanced, 0 position, Engineering PLA. So this is the scale, and this is the 0 position of the hammer, and this is the position after breaking the Advanced PLA object, and this is after Engineering PLA. And if I measure everything from the 0 position, I can use this information to calculate the breaking energy. And I believe that this experiment is most important for this video. So I have here the PLA Advanced and Engineering PLA, but for reference I added here just a regular PLA, PETG and ABS. And I want to record the temperature of the first deformation. PLA Advanced started with deformation somewhere between PLA and PETG, but later it slowed down and deformed after ABS test object. On Engineering PLA I noticed the deformation only at approximately 150 degrees Celsius. That was very impressive. The temperature is 173 degrees Celsius, and I will stop the experiment here. And I think it is quite obvious who is the winner, so this is very soft. So also the ABS shrink as always, and PLA Advanced just deformed, and the Engineering PLA just start with the deforming. Maybe you can see it from this angle, but it didn't deform completely. And our last view to this material, so PLA, PTG, ABS, PLA Advanced and Engineering PLA. The next is the creep test. The creeping is the deformation of the material during the constant load, and this is extremely important for me to see the real possibilities of this Engineering PLA. And since this creep test depends on the environment temperature too, and now the next 5 days will be quite hot, for between 19 and 35 degrees Celsius during the day. I will add for the reference, this is IZOD ABS Plus. And now adding the load. Well, for the side deformations, the weakest is the ABS, but I'm not surprised about this. As I mentioned, PLAs are very strong materials, but if we'll see, it will deform during the constant load. And for more accurate measuring, I am locking the position. 14.83, 15.33, 17.26. And I will measure this dimension every day, but off camera, and to you I will show only picture once a day. This is day 0, day 1 after 24 hours, day 2, day 3, day 4, day 5, and then I place the test objects in oven 1 hour on 50 degrees Celsius. So this was day 5, and this was after 50 degrees Celsius heating. And now removing of the load. And maybe this is an interesting information too, after approximately 15 minutes, and this is how they look. So I can see that both PLA have some permanent deformation until the ABS almost got back its original shape. And after 1 day. Now let's prepare the compression creep test. And now I will tie these bolts with this torque wrench, and tomorrow I want to see if I can tighten it more using the same torque, and I will measure with this angle meter. Now let's measure the additional rotation using the same torque. This is day 1 after 24 hours. This is day 2. This is day 3, which was very hot, 36 degrees Celsius max, and after this basically the creeping stopped. This is the 5th day now, and this is after heating on 50 degrees Celsius. And everything is recorded now, and it's time to analyze the results. And let's analyze all results in this Excel table, and I will start with the bending creep test. And these values actually are the distances between those two reference surfaces, but what we need are actually the difference between 2 days. And that's why I prepared this table. I calculated these values, and this will be presented in a graph. The screw type of the creep test is already in relative values, so 0 means no creeping, and I don't have to change anything here. Maybe one more thing I want to mention here, that for the layer adhesion test I will have another row, which is the Engineering PLA repeated with the specimens printed inside the enclosure. Let's see the graphs now. The creep test, the bending creep test. Actually all these values are very low. I checked the earlier videos, and only on 50 degrees Celsius inside the oven I can see a little bit more difference. The most creeping had the Advanced PLA, then Engineering PLA, and almost no creeping of the ABS. On a rotation or screw creep test, I can see that it slows down with the creeping. Interesting, on third day, which was the hottest day, 36 degrees Celsius was the max. Maybe that's the reason why we have additional bigger creeping here of the advanced PLA. But basically after fourth day, it almost stopped with the creeping, and even inside the oven, actually this is 50 degrees Celsius, it didn't have additional creeping. On a tensile test, the difference was very low. Now the layer adhesion test. It's really true that the advanced PLA have very good layer adhesion. Engineering PLA, basically everything above 20 kilograms is acceptable for me, and actually we don't have too big difference with this printing inside the enclosure. The shear stress, well, the engineering PLA was stronger a little bit, but the difference is not significant. The bending test was again very similar, only I can see that the engineering PLA resists more, so on this very similar load it deformed only 6 mm compared to the 10 mm deformations with advanced PLA. Now on impact test we can see very significant differences, so engineering PLA is extremely tough material compared to the advanced PLA or to other PLA materials. The torque test was very similar in both cases. And now this temperature test. I think this is the most important for these two materials in this video. The engineering PLA was very impressive. I noticed the start of the formations at approximately 150 degrees Celsius. That's very impressive. Now about advanced PLA, the first deformation I noticed was approximately at 55 degrees Celsius, but then it slowed down with the deformations and actually deformed completely after the ABS deform. Here you can see some repeated footage from that test. And now the conclusions. Well, actually I'm on holiday now, but everything was recorded before my traveling. And definitely the best PLA filaments I tested so far, with all those advantages which regular PLA have. So that's very strong material, except its biggest problem is the temperature resistance and the creeping. Now the PLA Advanced has extremely good layer adhesion. The temperature resistance is actually the start deformation was just a little bit above regular PLA, but then it stopped with deformation, and at the end actually it was stronger, better than regular ABS. PLA Engineering, great material, fantastic impact resistance, and also very high temperature resistance. So the deformations above 150 degrees Celsius, so that's incredible, and that's why I printed that fan shroud from our Prusa Maxi S from this material, because it is so temperature resistant. Now in both cases I noticed a little bit more stringing that usually I would like to see with the regular PLA. Maybe the reason is the moisture, because I noticed it just packed in regular foil without any silica gel inside. So definitely I would recommend to Filaticum to use some vacuum bags for the packaging, or at least put some silica gel inside these bags to keep it, to protect it from the moisture, because moisture actually can go through that foil. The creeping was not so perfect like with the ABS, but those results are great. For my Patreon supporters, they can compare these results with other materials, because they have the access to the Excel table where I put all the results into one place, so I can just save them some time to collect this data from different sources. That's what you can do. Every information is available to any of my viewers. Only you have to collect those data separately, file by file, from different videos. Well, I hope you find this interesting, this video. Definitely very interesting for me, because as I mentioned, this PLA engineering is extremely interesting material. Not so cheap, but definitely thanks to the printability and small shrinkage, so it has that dimensional accuracy. It is very interesting material for mechanical parts. If you have some other experience with these materials, you can write me down in the comment section, few lines. Thank you for watching and happy printing!